The last equivalence result that will be presented refers to the basis pursuit, in which an L1 regularization is used as a proxy for getting sparse solutions. The analysis that we are about to present is very different and somewhat more involved compared to what we have seen so far. Due to this complication, we break the description of this result into two parts. Here is what we are aiming for. Rather than solving P0, we will be solving P1, which is far easier to manage. We would like to claim that the shortest solution in L1, that is, the optimal P1 solver, is also the sparsest. If this is true, then solving P1 leads to the solution of P0. As we are about to show, this is indeed the case, but only if P0 has a sparse enough solution. We are given the matrix A and assume that B is obtained as A times a vector X, where X is a sparse vector. We start our analysis by defining a set C that contains all the possible solutions of the system AZ equals B that are leading us to failure. That is, this set contains solutions of the linear system Z that are shorter in L1 than the sparse vector X we started with. If this set is non-empty, then basis pursuit fails, because it will prefer an element from the set C over the original X. Therefore, everything that follows will be geared towards proving that under some conditions, the set C is in fact empty. Since this task is too complicated, our strategy will be to simplify C while inflating it, getting to a set that contains C and is simpler to analyze. First, let's redefine the set C by focusing on the difference vector E being Z minus X. This means that rather than seeking vector Z obeying the linear system AZ equals B, we seek vectors E in the null space of A. Note that with this change, we managed to remove B from our analysis. The newly defined set CE contains all the vector E that are in A's null space, and such that the L1 norm of X plus E is at most as large as the L1 norm of X. Note that the trivial vector X equals 0 is not permitted in this set. Again, if this set is not empty, then basis pursuit fails, since X plus E would be a better solution for P1. As we have already said, analyzing the set CE is too complex, and thus we seek to simplify it. We will focus now on the requirement AE equals 0. Our goal is to modify this requirement with a simpler one. Our first step is to multiply this homogeneous system by A transpose. The point to note here is that in doing so, the new condition on the vector E has not changed, since A is a full rank matrix. We proceed by subtracting E from both sides of the equation, and again, every E that satisfied the original condition satisfies this one as well, and vice versa. Now we take an absolute value on both sides of the equation obtained. Here, for the first time, we have modified the set. Every vector E in the null space of A satisfies the new equation. However, the reverse is not true. This means that our set has been inflated. The next step is a bit delicate. The right-hand side term has an absolute value of a matrix multiplying a vector E. We upper bound this by an absolute value of the matrix entries times the absolute value of E. The justification for this change relies on the triangle inequality, as shown here. The newly obtained condition has again modified our set and inflated it. Our simplification steps proceed, and now we look closely at the matrix that multiplies the absolute value of E. The term A transpose A should be familiar to you. This is the Gram matrix, known to have 1s on its main diagonal and values in the range minus mu to mu in the rest of the entries. Therefore, the absolute value of A transpose A minus the identity must have zeros in the main diagonal and values between 0 and mu elsewhere. This matrix can be upper bounded entry-wise by a matrix that has zeros in the main diagonal and mu elsewhere. This is written formally as a matrix of 1s minus the identity, all multiplied by mu. We build the matrix of 1s as a rank 1 matrix obtained by a column of 1s times a row of 1s. Again, this way we got a new simplified condition on the vector E posed in terms of its absolute values and the mutual coherence. We should note that there is an inflation effect in the resulting set of solutions compared to the original set we started from. This is the condition we obtained, and we proceed with its simplification. We open the parenthesis and observe that 1 transpose times absolute E is nothing but the L1 norm of the vector E. Rearranging terms, we get to this condition that ties the absolute entries of the vector E to its L1 length. Dividing by 1 plus mu, we get to the final form of this condition. We started from the condition AE equals 0 and ended up with the above inequality replacing it. In this change, the set CE has been inflated, and so if we could prove that the new set is empty, this implies that CE is empty just as well, thereby leading to the claim that basis pursuit succeeds in solving P0. The new condition we got is more pleasant to work with. We no longer see A, and the coherence is there to represent it. Furthermore, instead of E, we pose our condition with respect to the absolute values of its entries, a fact that will prove useful later on. So we summarize. We started with CE that contains all the problematic solutions the basis pursuit could stumble upon. We inflated it by modifying one of the conditions and got a new set that is slightly simpler to analyze. The new set is still unpleasant because it uses the unknown x in its definition. Our next step will be to remove its appearance somehow. Our set is defined over all vectors E such that when added to x, they decrease its L1 length or keep it the same. Writing this explicitly, we have this inequality. Let's break the summation into two parts, the on-support elements and the off-support ones. Note two things. First, as before, we should simplify our analysis by assuming that the on-support elements are the first ones. Secondly, in the off-support, xi are zeros, and therefore they vanish. We started with this condition and rephrased it to look like this. These two are equivalent, of course. Now comes the step of inflation. Relying again on the reverse triangle inequality, we lower bound the left-hand side expression by replacing the elements in the summation by minus the absolute of EI. Any vector E satisfying the original condition satisfies the new form as well, but not vice versa. And thus, imposing the new inequality, we have inflated the set. Rearranging terms and adding and subtracting the sum of absolute EI over the support, we get to this final term. The L1 norm of E should be no bigger than twice the sum of its absolute entries on the support. In our notations, the vector 1s stands for the vector that contains 1s on the support elements and zeros elsewhere. We started with this condition and ended up with this alternative. The newly defined set of vectors E is bigger and contains the original one. The new set is much better posed for our analysis because there are no appearances of A, B, nor X. Only the support and the coherence are used for its definition. So is this set empty? We will explore this in the next part that follows immediately.